Hi and welcome. My name is Andrea Weidlich. I am a principal researcher at NVIDIA in the Real-Time Rendering Research Department, and I'm also the organizer of this year's practical aspect of spectral data in digital content production course. This is a second iteration. We had already one course last year, but this year's focus is more on the application side. We established the theory last year, so this year we have to focus on how to combine spectral and RGB data so they can enhance each other and improve workflows. The first part of the course will give you an introduction of the topic of spectral rendering. So if you haven't heard anything about spectral rendering so far, this is for you. If you're already a pro, feel free to skip it, although I think there might be a couple of things you might still find interesting. I will never know if you skip, so feel free to do. Otherwise, I would say let's dive straight into spectral rendering. We have two renderings here. Typical scene, path traced, many lights, so it's not entirely the easiest things. One is RGB, one is spectral. If I wouldn't tell you that one of them is spectral, you most likely wouldn't know. So there are two things we can learn from this. One, spectral rendering is not slow. People often think it is, but I think I can prove it with this video that it is not. It has exactly the same performance as RGB rendering. And the other thing is that spectral rendering can look exactly like RGB rendering. So what is the hype about? Why, for example, did Wētā Digital as a studio to decide to fully switch to spectral workflows a couple of years ago? The first thing people will normally think when someone says spectral rendering is diffraction or dispersion, wavelength effects, wave optics in general. So this is definitely a spectral thing, so this is a reason why you would want to have spectral rendering, but it is not the reason why you should switch to a spectral renderer, because primarily spectral rendering is about color fidelity. It is important for nonlinear effects. So what I have here is absorption, water properties which you can find in literature, and if I switch between RGB and spectral, so you can see that the color changes, although for the short bounces, the short way, it is exactly the same thing. So first example of why color starts to change. Then there is also scattering, multiple bounces within fur, interreflections of metals, wherever you have light bounces that will accumulate the same color again and again. So typically what happens in path tracing, and this is exactly the thing why spectral rendering becomes so important in the context of path tracing. And yeah, the other thing we like about spectra is that spectra are a physical quantity. They are something which are independent from observer and from display, and they have a meaning. So for example, this is the classic chromaticity diagram you have. If I take Macbeth color values, they can be measured. They have a reflectance curve, and that one can be measured, and it is an absolute response independent from the light, and gives you how much energy is reflected for a certain wavelength. So there is no dependency on anything. An RGB color, on the other hand, that one will always depend on the white point, it will depend on the color space you are in, and so it is a relative quantity. Due to the fact that you can measure spectra, that makes it very convenient for content production, because you can measure lights, you can measure cameras, you can measure gels, you can go to your favorite vendor and say, this is my light source, sell me some device which can give me the property of that light. And this is so important to guarantee reliability. Color reliability is something very important when you do content production, and that's the reason why everyone there is so fond of it. To give you an example, this is especially important when it comes to camera. So if we go back in time, that image is a very old makeup instruction sheet. It's from 1914. And what you can see if you take a close look is that there are very, very weird colors described here for the makeup. Purple, blue, yellow, so nothing you would normally connect with makeup. The reason for this is that cameras, black and white cameras, have a very strange response when it comes to the red tones. And in particular, everything will become one mushy color. So by using different colors there, you can bypass that issue. And since the internet is very large and people are bored, this is how it would look if you really would apply such a makeup. There was this film from Apple last year, which was a black and white film. I would love to see what kind of images they had. It's very hard to get behind the scene materials, which is not black and white. I know that they did the costumes in black and white. It would be highly interesting what they did with their makeup. So if you have worked on that thing, feel free to reach out to me. Yeah, but let's go back to Spectra. A spectral rendering framework is not that different if you compare it to an RGB framework and an RGB renderer. So I would say let's demystify spectral rendering here and look at what is needed to make a spectral renderer spectral. So there's a very coarse classification where you can say it's input, then you have the rendering, the light transport stage, and then you want to output your data again. So the input stage, in my eyes as a material person and a person who has spent a lot of time with appearance, it is the stage of spectral rendering which is not, or is at least explored. So the core problem there is that you can no longer put RGB data into your renderer. So you need to feed spectral, you need to produce spectral data because the renderer will use spectral data as a quantity during light transport. So the core problem there is how to get the data into the renderer and where to get the data from. Spectral BSDFs, at this point, they're optional. You can, of course, do all those wavelength effects, but really they are not a necessity for a spectral renderer. Quick exploration on how spectra look. For those of you who have never seen spectral data, there is a very coarse classification into two groups. One is the group of smooth spectra, the natural spectra. Normally you would say, so anything, pigments, leaf, chlorophyll, these things, they have a very smooth curves. And in contrast to those, what we call artificial spectra. So spectra of light sources, of elements which exhibit peak structure, so a discontinuity and spikes in their shape. Orthogonal to both of them, fluorescence data, it's special, and so it's not that much about the shape here of the spectrum, more about the fact that you need a two-dimensional data structure here. So one which encodes the absorption and one which encodes the re-emission of the data. So the first job of us is now to get that kind of data into a renderer. The easiest thing is, of course, to measure something real world what you have. You tabulate it, you store it, and you're done. The disadvantage of this is that the color of your object will be constant. And while this is okay for reference objects like Macbeth color charge or these gray balls you can see in movie productions, it is normally not what you would need in content creation. Fun fact, apparently the Macbeth color chart changed in 2014. So when you have one, you should take care that you get the measurements, the reference values for the one you have and not the other one. So content production, again, needs textures because textures are what makes things interesting. For us, this means now that every pixel will need a spectrum. And as you can imagine, that means that the memory increase is quite substantial. So if you look at this texture here, it's a very, very, very small patch, and it becomes already a huge block of data. If you have a texture, a simple text file is most likely not enough. So there are various methods on how to store or encode a spectrum. The classic variant is to do point-based sampling. So in a uniform density, you start taking samples from your spectrum and encode those. You could also use basis functions. Those were quite popular in the 90s, early 2000s. Hybrid approaches where you would use both different kinds of storage means, like basis functions and point-based, or Gaussian mixture, for example. And then there's, of course, neural networks you could use to encode your spectrum. So especially the last category is not really explored, what it can do, how powerful it is. So there is definitely more work to be done on this frontier. The most popular version to do the most popular storage mechanism is point-based sampling. Because it is simple, because from a mathematical point of view, it is very self-explanatory and easy to handle. People don't only store input formats as a spectrum. Sometimes it is necessary to encode it inside the renderer as well. Manuka, for example, the renderer from Wētā Digital, it uses point-based sampling to store heterogeneous volumes inside in the binned version. There are spectral texture formats available, not a lot. The most useful ones for the content creation line is most likely the extension through OpenAXR, or there's also a TIFF version. They both work in a very similar way. So there is one channel which encodes the final image as an RGB, so that you can read it. And then there is additional data as point-based samples stored. The vision community is quite fond of hyperspectral textures. They use mostly a proprietary format, HSZ, for their purpose. There is also the AXF format from X-Rite, but that one is more an appearance format than a spectral texture format, and it encodes a whole spatially varying BSDF. So spectral data, spectral textures, they are great, but they have true drawbacks. So one is the acquisition. It is really hard to get them. Taking a photo is suddenly not enough. Plus memory. So they will need a lot of memory to store all the data. Still, we do need a lot of them because production assets, production scenarios, they are very complicated. So I have here an image from a small patch of skin, and you can see there's a lot of things going on. So there's some water on it, and there is some dirt there. There's some paint and the skin itself. So everything here needs a texture. And this means that the memory becomes a concern quite quickly, and you need to see how you can manage that. That's the reason why in content production, uplifting is the weapon of choice. Uplifting is a technology where you take an RGB value and you convert it to a spectral curve. So you don't measure the spectrum directly, you come up with the value from the RGB data. And those are, what you get there is a metameric spectrum of the color you want to have. The issue is that you can have for one color, in theory, an infinite number of possible spectra, and your uplifting method can only give you one specific curve, of course. This also means that the round trip, which is the quality thing you're after in the uplifting, that one there, the uplifting algorithms, they are targeted for D65. And if you look at the comparison I have here from different skin colors and uplifted to a spectral curve, all of them have an almost perfect round trip in D65. The situation changes if I switch to a fluorescent light source. In this example, I used F12, which is quite a spiky light source, and so you can see differences in the color there. So does it mean that one of them is worse than the other? Not really. As I said, it's a metameric thing. The benchmark for uplifting algorithms is this Macbeth chart. So whenever someone comes up with an uplifting algorithm, they will try it on this Macbeth thing, and then they will have a judgment if it's good or not. No one, for example, is using it on a bigger one. It's like this many patches you have there, which has some very interesting features. For example, those 3 patches there, which look almost identical. But if you look at the spectral curve, the curve is quite different. So bottom line is that uplifting is great because it means that you can still utilize your RGB workflows. You can still use painting tools, texture compression, mip-map filtering, all these things without having to deal with the spectral form of the data, but still creating spectra. The drawback is that the spectrum you get is not necessarily the spectrum you want. A way out of that is target-based uplifting, so that you say, oh, I have prior information of what kind of spectrum I want to have. And then you tell your algorithm, for example, it's supposed to be a skin spectrum. And then the curves you get out of that one are almost entirely a perfect match to the curves you want to have, which also means that if you start changing light sources, you go, for example, from daylight to LED light, your spectrum or your color will still match. The disadvantage of those algorithms is that they are quite clunky most of the time. They are not as fast and they are difficult to handle and set up. So in the beginning, we looked at the physical meaning of spectra, and I said like they're the real deal, so which means that they can simulate all visible colors you have, and they are not limited to a color space and everything. And this is correct, but only half correct, because we can have all colors with spectral rendering, but not in all brightnesses. So there's one fundamental problem with color and spectra. A reflectance spectrum cannot exceed 1, and this limits the amount of saturation you can have in a reflectance spectrum. So in this example here, every single dot in the chromaticity diagram represents a Gaussian spectrum. So it's a single Gaussian with various mean and various sigma. And the smaller the sigma is, the more saturated your color will become. So for example, if I take this point here, it's a nice green, not particularly saturated. If I want to saturate it now, I will make the Gaussian curve slimmer, and what we can see is that the point starts to move towards the edge of the chromaticity diagram, which means it will become more saturated. But on the other hand, if I go further and further, it will become darker and darker. So this part is the solid gamut of the gamut of solid reflectance colors, and it means that you cannot have a very saturated spectrum that is bright for reflectance colors. The way out there is to make use of fluorescence, so to say I am now legally allowed to exceed 1, and I do this by justifying it with fluorescence. So at this point you can have very saturated spectral reflectance colors, but it also means it comes with a performance hit. So let's go back to the rendering pipeline, I would say. Now we have just put in our data, we are fine there. The next step would be light transport. And that is surprisingly simple, because the only thing you need to do there is you need to save a wavelength in your path space, and then you can take one of your traditional RGB components as the wavelengths and use that for tracing, and that's it. So there is this common misconception that spectral rendering is slow and it is difficult to implement, and in fact none of these things is really true. What you do is you would have your normal RGB renderer, you remove 2 of the 3 components, you say now stochastically I use a wavelength, I choose a wavelength, and then you start again and again for each path in path tracing to use a different wavelength until you significantly converge. Now the issue there is color noise, because all of a sudden we need to integrate over another domain, and this means that you can reduce the color noise if you use more samples, but it is still color noise. It is still one source of Monte Carlo noise. A way to increase performance at this point is if you trace multiple wavelengths at the same time. This means that for the cost of one trace, you can evaluate multiple wavelengths. This is called Hery wavelength spectral sampling. We will hear more about this topic in the further along in the course. And yeah, what you do there is you just, for every wavelength, you also sample 3 more and trace those at the same time. The original paper proposed to use 4 wavelengths. So why 4? So that for every sample you use 4 of them, because it's the best, it was back then the best trade-off between what you pay for it and what you get out of it. For the sake of implementing a spectral renderer, you can also use 3, and this means that your existing float 3 in your RGB renderer can be used as a data structure. So let's go back to the scene from the beginning. So both of them are spectral, both of them look pretty much the same. If you look at the green rectangle there, you can see that they converge in a different speed. And the reason for that is that they use a different light source. So one of the light sources, the one to the left, is smooth. The one to the right is again a fluorescence F10 light source, so quite spiky. And this means that the spiky one will take a lot longer to converge because the Monte Carlo approach has a harder time to find the high energy wavelength. What we can learn from this is that not all spectra are equal. Especially for Hery wavelengths, what you have, since the samples are uniformly chosen, monochromatic lights, fluorescent lights, they will have some issues there, and they are harder to converge. So that is the part where Hery wavelength, or where wavelength importance sampling comes into play. So instead of sampling them uniformly, what you do is you bias where you want to sample your wavelength. And there are various approaches for that. Again, more about this further along the course. You can pre-analyze the image, you have the continuous multiple importance sampling. And yeah, so there is a solid amount of work to be done, which was done there, and which most likely will be done in the future. So that was the magic of spectral rendering. Yeah, bottom line, if your renderer can do RGB, it can also do spectra. The part where we need to do something again here is now the output part. So how to get the image out of the renderer. So there is the main thing, the camera response. You rendered now in spectral. So what you have is the representation of light transport in a spectral format. And you want to get that one into an output representation. So what you need to do in a nutshell is you take your frame buffer, your final result, whatever, and if you happen to have a spectral texture as an output format, this is everything you need to do. You're done. Most of us most likely will not be happy with that, and we need a final RGB representation. So what we do instead is we go through the XYZ. We use the XYZ curves and convolve it with the spectrum, and then we have the XYZ values, use a matrix to convert to RGB, and voila, you are in RGB. So those matrices, they can be found in literature, they can also be derived. For content production, for movie production, XYZ is, again, it's great, but not really what you need. What we are after here are camera spaces. So what we do here is, instead of using XYZ curves, we will use camera profiles. Every camera comes with a specific camera profile which can be measured. And we use these profiles to simulate what the camera would see. So again, we take those curves, we get into camera RGB, and then instead of using the XYZ to RGB matrix, we will have a camera to XYZ and XYZ to RGB matrix, which we use in that. The advantage here is that you can simulate what a camera can see, which means that you really have the real deal there. That image is from last year's course. So what I have here is 12 objects at the top. All of them are gray, although they have a different spectrum. This is what we call metamerism. So they are metameric in D65 in XYZ. Now, if you happen to use a different camera, cameras which are normally used in movie productions, the result will be different. So you will suddenly start to see that the spectra of the objects, that they are different. Thing is that this is a little bit of a contrived setup. So if you look in a more realistic scenario like what I have there, the difference between the camera and the XYZ, for example, is not that big. I mean, it is there. If you look at the comparison, it's most probably nothing which will keep you like an O and R. Yeah, just to give you grounded in what it is. The reason why those things here, especially these rows here, are so different, is that they have a very discontinuous spectrum. So the less equal your spectrum is in energy, the more shapes it has and structures it has, the more visible your result will be, and the more visible the difference will be if you switch camera types. And in the scene before, I happened to use a very flat spectra without any remarkable structures, just to emphasize that you don't have to see a difference if you switch cameras. So what's left to do? Denoising, for example. It's one thing that got little attention so far, how to denoise a spectral data, because they do have color noise and the noise profile is quite different from the RGB one. So I have two renderings here. The top one was trained with RGB data and the bottom one with spectral data, and it can be seen that by training them differently that the noise visibly reduces. So denoisers will definitely need to be revisited. Yeah, and that's pretty much it. This is what you do, what you need to do to make a spectral renderer. What can we learn from this? First, spectral rendering is it comes with a lot of advantages and hardly any disadvantages. Of course, there are many things you need to do that will need more research. For example, better uplifting. There is the texture, spectral textures. That one is not good explored well. The whole question of how can you art direct a spectrum, like increase the saturation, decrease the change the hue, these things which you would do, changing pipelines, how to compress data, and so on. But yeah, the question you have to ask yourself here is not why you should not do it, but why you should. In the future, of course, we hope that we can go towards wave optics, like the full-fledged things, the ones you see in the research community. But right now, this is unfortunately out of scope, but we hope that eventually we will be there. And this concludes my part of the course. We have more to come. There is the next one in line is Chloe from Netflix. She will talk about multispectral lighting reproductions for virtual production. And she will talk about color rendition properties of LEDs in virtual production. And then we have Carlos and Christophe, they're from Weta. They will share the experience with digital humans and the importance of spectral data in their creation and how you can derive a correct spectrum from RGB photos. Then we have Jean-Marie and Jirí from Wētā Digital. They talk about sampling and resampling and spectral rendering, their experiences on how to reduce spectral noise and how RGB techniques like guiding and raster can be used in a spectral renderer. And lastly, Daniele and Richard there from Filmlight, they tell us about spectral data in comp and how spectral intermediates in their grading workflows work in their talk about grading movies using a smooth spectral intermediate. And that's it for me. I thank everyone who made this course possible, and I thank you for watching it, and hopefully see you soon.
Hi everyone, my name is Chloe LeGendre. I'm a research scientist at Netflix. Today I'm going to be talking about multispectral lighting reproduction for virtual production. Now before I get started, some of the content I'll cover in this course was completed during my time at USC's Institute for Creative Technologies, while some was completed more recently while working at Netflix. This lecture is part of a broader SIGGRAPH 2022 course titled Practical Aspects of Spectral Data in Digital Content Production. And now, of course, when we think about spectral data being used for content production, we're usually thinking about this in the context of using a rendering engine. But in what I'll talk about today, which is virtual production, the world acts as our spectral renderer. The kind of virtual production I'm going to talk about is when you surround actors with light sources representing the illumination of either a real world or a virtual scene. Here we see a modern example of the technique being used to produce the new Netflix show 1899 on the set of the Dark Bay facility. We have here a combination of LED panels arranged in an arc, as well as other light sources on the ceiling that surround both the actors as well as the physical set from all directions. Now, there are three main benefits to filming in such a virtual production stage. You may also hear these referred to as LED volumes. First, you can film what's called an in-camera background. In this scenario, the LED panels replace the need for a green screen, and so the LED pixels, they display the background content, and they're directly recorded by the motion picture camera, as you can see in this example. And this removes the need for post-production matting techniques like chroma keying, rotoscoping, or more generally just compositing. Next, the actors, while still performing inside a studio, they get the opportunity to perform in an environment that resembles the real world. This has the potential to enhance their performances and even to provide consistent eye lines for different actors. But finally, the main advantage, and the one that we're going to be focused on today, is lighting reproduction, where the illumination on the actors matches that of a real-world or virtual environment, and you're using the LED stage to directly reproduce a scene's lighting. In the original image that I showed here, you can see the virtual production stage producing kind of a cloudy daytime environment with relatively diffuse lighting from above. Although this version of lighting reproduction leverages both LED panels as well as other cinema light sources, at SIGGRAPH in 2002, Debevik et al. Introduced a first lighting reproduction solution where an actor was surrounded by a sphere of computer-controllable red, green, and blue LEDs. These LEDs were driven using RGB colors of photographed high dynamic range lighting, or by using the light from a virtual set, enabling seamless integration with computer-generated scenes. Since its introduction, the technique was applied in many movies, including in Gravity, where actors were surrounded by a whole box of RGB LED panels that displayed pre-computed dynamic lighting from virtual scenes that were used to light the actors. And this was kind of the predecessor to today's LED panel-based approaches. It was also used in Rogue One, where HDR virtual lighting environments were displayed on LED panels to light real actors inside this constructed ship cockpit. Now, with travel restrictions in place due to the COVID-19 pandemic, many other examples of film and TV using this technique have since emerged, and this is nowhere near a complete list of projects that use the methodology. However, in each of these projects, they all used only red, green, and blue LEDs. Now, we know this already for the light stage version, but if you look very closely at an LED panel that's used in typical virtual production stages, you're going to see individual pixels represented by single red, green, and blue LED units, as we can see in this close-up photograph here. And since your panels are RGB and your photographed or your rendered lighting environment is also RGB, then you can just drive the LEDs of your light source with the pixel colors of your lighting image, possibly first after applying a 3x3 color matrix. And this works reasonably well in practice because RGB LEDs can produce light of almost every human observable color. But the problem that we're going to talk about today is that they can't produce light of any spectrum. RGB LEDs unfortunately have relatively peaky emission spectra, as we can see here for each of the red, green, and blue LEDs for a given pixel. And although this isn't an issue when we're using these LEDs as a display, we have to think about what happens when we want to use the LED panels as light sources. In 2003, Wenger et al. Tried to use RGB LEDs to reproduce the spectrum of real-world illuminance, like an incandescent and tungsten source, which has a spectrum that looks something like this. Now, unfortunately, you can't match this spectrum exactly using just RGB LEDs because you can't combine these three spectral peaks to match this spectrum of tungsten. Now, to visualize what this meant for color rendition, Wenger et al. Demonstrated that trying to match both a tungsten and fluorescent light source using only RGB lighting didn't work very well in practice. So in this image, the subject is lit from image left with a tungsten bulb and image right with a fluorescent bulb. And this second image here shows a reproduction of the illumination using RGB LEDs, where the goal here was to match the spectra in a least squares sense. And we can see that this really didn't go very well. Wenger et al. Also tried to match the color of the lighting rather than the spectrum. And while the results look overall better, the colors still don't match here. This is most obvious for the denim jacket, but it's also true of the skin tones as well if you look closely. Now what's happening here, and this is really a key point for the course today, is that the world is acting as a spectral renderer. Pixel values are produced by integrating over all wavelengths a fully spectral modulation of a seen illuminant by the reflectance of the material being illuminated. In this case, we're looking at a reflectance spectrum for skin. This is integrated against the camera spectral response for each color channel. And with LED reproduced illumination, the colors are going to be different whether we try to match the spectrum or the color of the original illuminant. It's really these spectral mismatches that matter for color rendition. Particularly, the dip between the green and the red LEDs at about 550 to 600 nanometers is especially problematic. This does matter when we're looking at skin tones, but it especially matters when we're looking at yellow and orange materials. We're totally missing energy in this yellow part of the spectrum. And the result is that yellow materials often disappear when they're illuminated within virtual production stages. The image here on the left shows Paul in his Hawaiian shirt under a broad spectrum warm white LED. And on the right, we can see the appearance of the shirt under an RGB LED virtual production stage that's trying to reproduce this illumination. In this case, we've matched the color of the light, and so the white balance here is the same. So Wenger et al. In 2003, they thought about adding LEDs to fill in these spectral gaps for an individual light source. Now, fortunately, other LEDs besides RGB are available. And Wenger et al. Built a 9-channel light source out of color kinetics lights in order to compare with RGB LED lighting when used for lighting reproduction. Now, notably, in order to achieve these kind of yellow colored sources that you can see in the image here, they had to place yellowish gel filters over white LEDs. And although lots of different LEDs of distinct spectra are available, kind of making these yellow looking LED lights emitting light around the 550 nanometer region was difficult then. And indeed, it's still difficult today, which we'll see later. Now, to figure out how to best drive these LEDs to reproduce a light source, Wenger et al. Introduced 3 approaches that were all based on spectral measurements. We already saw the first 2, but I'll summarize them. First, in what they call spectral illuminant matching, they minimize spectral error directly for a target illuminant. Next, in what they called metameric illuminant matching, they tried to match the color of the target illuminant, which requires a specific observer or camera because color is in the eye of the beholder. Now, the target and the reproduced illuminants here are called metamers. In color science, this refers to 2 colors that appear the same despite having different spectra. And we saw results on previous slides that were using these 2 techniques. But finally, in the third technique that they introduced called metameric reflectance matching, they tried to match the color for a whole set of materials lit by the target illuminant, and this of course also required an observer. When trying to reproduce illumination using LEDs, for all 3 spectral matching methods that they introduced, the 9-channel lighting that you see here on the top vastly improved the color rendition compared with the RGB lighting alone that you see on the bottom. Now we should note that Wenger et al. Here used spectral measurements for each part of the system in order to achieve the results. This was a great proof of concept for improving color rendition using a multispectral light source, expanding upon using RGB-only LEDs. However, this test covered only single light sources, and for lighting reproduction and virtual production more generally, we'd ideally like to get this benefit from all incident lighting directions. In fact, even to generate these figures, the subject had to stand very still while a light source was manually repositioned to her left or right. With this in mind, at USC ICT, we built a fully omnidirectional multispectral light stage. And you can see it here. We're peering into the stage here using a wide-angle lens. This stage added amber, cyan, as well as broad spectrum white LEDs to the original red, green, and blue of a lighting reproduction system to try to fill in these spectral gaps inspired by Wenger et al. And the spectra for these new LEDs are shown here. So each one of these hexagonal stars that you can see in the cluster is a custom-built circuit board that was used to drive the different channels of LEDs. Now, at work that we presented at SIGGRAPH in 2016, we tried to answer the following question. How does one drive multispectral lights to replicate real-world lighting? And in particular, how does one use 3-channel RGB light probes to drive multispectral lights that have 6 or even more spectral channels? So in the most kind of straightforward approach, we could just point a spectroradiometer, which is a spectral measurement device, in every direction for which we have a light source inside the light stage. And then we could imagine just mixing the LEDs to best match this measured illumination spectrum. And this would essentially be borrowing the spectral illuminant matching technique introduced by Wenger et al. In 2003. However, this process would be slow and cumbersome. So instead, we thought about another way that photographers capture color rendition, and this is by photographing a color chart. In the color chart, each chart square has its own unique reflectance spectrum that tells us something different about the spectrum of the scene's lighting. So in our approach, we're going to directly solve for how to drive the multispectral LEDs of our light stage to match a given color chart's appearance. Take as an example a color chart that's lit by a particular target illuminant, say tungsten. What we do is we first photograph the chart lit by the red, the green, the blue, the cyan, the amber, and the white LEDs inside our light stage. And now we know that any color chart that's going to be illuminated by a light source in the light stage is going to have to be a linear combination of these 6 images because light is additive. So what we can do is just solve for the amount of each image to add together to produce the appearance of the chart lit by tungsten. And then this corresponds to the intensities that we use to drive each LED. Now we're happy because this technique doesn't require any spectral measurements. So it's actually the same process as the metameric reflectance matching technique of Wenger et al. 2003, but with no spectroradiometer required. At this point though, we need to think about how do we use this step or this process for every light in the light stage for the whole sphere of lighting directions. So in this work, we introduced the idea of a color chart panorama, which is a record of the color rendition properties for each direction in a given scene. We also introduced 2 capture techniques to measure this information. In the faster technique, we photographed an arrangement of 2 reflective spheres and 5 color charts facing in different directions using multiple exposures. The chrome ball here on the left records the color of the incident illumination from every direction, and the black sphere on the right gives an image of the environment about 4.5 stops darker if we want to shoot HDR video. The 5 color charts in the center yield low angular resolution spectral detail of the illumination. I'm going to skip the data processing technique and move straight to results where we capture lighting using this system, and then we play it back inside the multispectral light stage in order to light a subject. Now in the images that follow, we've applied no image-specific color correction. These are just results coming in camera, just converted to sRGB only for display. So what we've done is we first photographed our multispectral light probe and 2 friends of our lab, Janetta on the top and Jessica on the bottom, in a real mixed illumination environment. We then reproduced the illumination inside the light stage using 6 spectral channels, and we observed close visual matches. We also observed close visual matches using only RGB and white LEDs. However, when we use RGB only lighting, skin tones appear the wrong color. They look overly saturated and they look hue shifted, consistent with what has been observed in contemporary virtual production stages. We also captured a lighting environment outdoors that included direct sunlight, photographing Janetta and Jessica here again as well. We produced close matches using 6-channel lighting in the light stage and even 4-channel lighting using RGB and white LEDs, which might be acceptable for many applications. And once again, RGB only lighting leads to color rendition challenges, especially for the skin tone of Janetta in the top row. If we look at a color chart, we see the same pattern. Here, what we've done is we've sampled pixel values from photos of color charts lit by 3 real illuminants, tungsten, fluorescent, and daylight. And then we photographed color charts lit by the LED reproduced illumination for different combinations of LEDs. When the dots, which are the LED sampled values, when those fade into the background, it means we've achieved a very close visual match. So here we can see that using 6 LEDs gives the best color rendition. However, using RGB plus white already looks significantly better than using RGB alone. Now, the relative success of the RGB white LED mix here brings up the next question, which is what's actually an optimal LED selection for lighting reproduction? How many spectral channels do we really need for color accurate lighting reproduction? Instead of 6, can we use 5? Can we use 4? How many spectral channels do we need? Is there any point in adding any more? So our intuition tells us that adding more types of LEDs with different spectra is going to improve our ability to reproduce different illuminants, but we don't really know if this is true. Furthermore, which LEDs should we choose? Which ones are going to be the most useful? In our light stage that we just showed, as well as in the 9-channel light made by Wenger et al., the selections were just made based on the heuristic that we wanted to cover the most of the visible light spectrum. But is there a better combination? So to answer these questions, if we answer these questions, there's applicability, of course, in light stage type system design, but also more generally for studio lighting design and any color sensitive imaging workflows like archiving and cultural heritage preservation, for instance. So fortunately, in the time since Wenger et al. Was published with their 9-channel light, there are newer LEDs of unique spectra that are available. And in particular, you can find LEDs of the colors lime and PC amber, which stands for phosphor converted amber. Similar to white LEDs, these use royal blue emitters that have emission broadening phosphors in front of them. But unlike white LEDs, these new colors, the lime and PC amber, have essentially none of the blue emitter output remaining. And although they do fill in the spectral gaps in the kind of yellow-green region, if we look at their relative energy output compared with other colors of LEDs, we can see that they're still fairly dim and they have broader emission spectra as well. So in total, there are about 11 different LEDs of distinct spectra that are available. They have emission spectra similar to those that you can see here. And there are some slight adjustments and there are more that are in the IR range, but this is kind of the ones that span the visible spectrum. Now for our optimal LED selection, we're interested in using these LEDs as sets, say of 4, 5, 6, or maybe even all 11 of these available LEDs, for instance. And so there's a lot of possible combinations here. So if we're going to look for 4 sets of LEDs, then we have 330 options. If we're going to look for 5 LEDs, then we've got 462 options, etc. So our goal, again, is to be able to reproduce certain common illuminants inside a lighting reproduction system. And so we wanted to consider some standard illuminants like tungsten, daylight, skylight, which is the sky without the sun, as well as a fluorescent spectrum, sort of some logical choices. However, light sources in lighting reproduction systems are often responsible for reproducing indirect illumination as well, such as sunlight bounced off of sand or greenery. And so we also considered here sunlight as modulated by the reflectance spectra of grass and of sand, which are important because of their prevalence in natural scenes. So here what we're going to do is look at color charts generated for a standard observer for each of these 6 kind of test illuminants. And again, the background squares are going to represent the color chart seen under the true illuminant, and the foreground dots represent the best lighting reproduction result for the specific LED combination. And so you can see first the results for the RGB only LEDs, and as we expect, they're not very good. Next, we can add the white LED. The fluorescent and the tungsten here are particularly challenging to reproduce, but the others are starting to look okay. If we add the PC amber, the phosphor converted amber, the dots are barely observable at all. And finally, here's the result of using all 11 LEDs of distinct spectra. And there's almost no perceivable difference between using all 11 and using 5 LEDs. So to summarize, we see that we get very little improvement when we use more than 5 spectral channels in a lighting reproduction system. And this kind of goes against our intuition that just continually adding more spectral channels is going to improve our color rendition capability. We also found that our optimal light source should include RGB white and PC amber LEDs. This combination ended up as the winner when we considered all the different error metrics introduced by Wenger et al. For the human observer, for different cameras, looking at the color chart spectra, looking at skin tone spectra as well. Now, if we wanted to add a sixth LED, we found it should be either lime or cyan. So we made a plan to incorporate the results of this analysis into our next generation light stage designs. And in particular, USC ICT designed and built a multispectral lighting reproduction rig for Suvi, who are a Beijing-based media production company. The Suvi light stage was the first 8-meter dome designed specifically for lighting reproduction. The light sources are similar to those in the multispectral ICT light stage that I showed earlier, except that our previous work informed the swap from kind of a narrow band amber to the broad spectrum PC amber that I showed the spectrum of before. And in addition to the dome lights that we've seen before, this light stage also has a light up floor. And you can see the floor here lighting up in different colors looking through a fisheye lens here. So although we're very thrilled to have been able to build this multispectral light stage for lighting reproduction, in the years since its construction, we've seen a huge increase in virtual production just using RGB LED panels. And so understanding that this is kind of the state of the world today in virtual production, when we got to Netflix, we wanted to ask, how can we improve color rendition when we are using just RGB LEDs? So let's assume that we're going to leave the hardware the same. Now, if we time travel back to SIGGRAPH in 2016, when I first presented our work on the multispectral light stage, a very astute audience member who will go unnamed asked me, well, what if you allow for post corrections? Will that help improve color rendition when using only RGB LEDs? Unfortunately, at the time, we had thought about this ahead of time, and we had come prepared with this visual answer. Compared with using RGB LEDs to reproduce common real-world illuminance, applying a color correction transform in the form of a 3x3 matrix does allow you to improve the color rendition. Here again, the foreground dots are colors sampled under a reproduction of the illumination shown over the background squares, which are the colors under the real-world illuminance. Now, we see this improvement using this 3x3 post-correction matrix, which you see in the second row here on the slide. If we compare this, however, with a fully multispectral approach, we do see that this post-correction matrix result is not quite as effective. But nonetheless, this post-correction matrix idea did help. So this inspired our latest work at Netflix, which we'll be presenting this year at the DigiPro Symposium that's co-located with SIGGRAPH. So to start, we need to consider what people are doing now to calibrate their virtual production stages, specifically looking at color. So the first thing that they do is they typically ensure linearity. So a pixel value that's twice as bright as another produces twice as much light when both are displayed on the same panels. Now the next thing that you might do is to measure the LED primaries as they're seen by your camera and make sure that a red pixel value in the content that's displayed by the panel looks red to the motion picture camera, and then the same thing holds true for green and blue. Now this is typically achieved by generating a 3x3 color calibration matrix that we'll call M as in Mary, whose job it is to make sure that a primary displayed by the panel actually looks that color to the camera. In practice, this 3x3 color matrix is applied to the content before it's displayed by the panels, and so we can think of it as sort of a pre-correction matrix. Now the nice part about this process is that if red, green, and blue look correct to the camera, then all the other colors in the content, including white, will look correct as well because they're all linear combinations of the primaries. So this process is great, and it works very well if your goal is to make in-camera backgrounds look correct. But what about our post-correction matrix now? So if we apply a post-correction matrix Q to the final image, let's say it's a 3x3 matrix, although the foreground content will be a closer color match, the calibrated in-camera background that we just spent this time calibrating the primaries for will no longer appear correct. Now, we could imagine a world where we first perform a foreground-background segmentation and then we apply our post-correction matrix Q only to foreground pixels. But this really defeats the purpose of virtual production, where we're trying to avoid segmentation in favor of filming the background directly in camera and not needing to do any matting. So our key insight in this new project is that we can apply a different panel calibration matrix to pixels that will be observed directly by the camera, treating in-frustum pixels differently from out-of-frustum pixels. Since most virtual production stages already leverage camera tracking for parallax adjustments, this is straightforward to implement because you can already separate in-frustum and out-of-frustum content. So instead of applying our original color calibration matrix M, as in Mary, to in-camera frustum pixels, we're going to apply the matrix N, as in norm, which is the original calibration matrix multiplied by the inverse of the post-correction matrix Q, which you can see the formula for on the slide. If we know Q in advance, then we can solve for N, as in norm. And because the background pixels don't contribute very much towards the actual lighting on the actors, now both the foreground color rendition as well as the appearance of the in-camera background are going to be near optimal. That was a big wall of text. So to visually summarize the approach, instead of using this wall of text, we have three matrices now in our pipeline. Matrix M, as in Mary, transforms the pixel values of the content to values that are going to be shown on the LED panels outside the camera frustum. This is the same matrix that's used by today's in-camera VFX calibration workflows, so the primary based method I showed before. Matrix N, as in norm, transforms pixel values of the content to pixel values shown on the LED panels inside the camera frustum. And finally, the matrix Q transforms pixels recorded by the studio camera to the final pixels to be displayed on the set and then sent to editing. The in-camera matrix N is different from M because we know ahead of time that we're going to post-correct the whole image after the fact of capture with Q. So we're going to essentially make the in-camera background look wrong on purpose because we know we're going to correct it later. So to test out this approach, we captured 7 different spectrally diverse lighting environments in the real world. 2 were outdoors in the sun, 1 was in the shade, 1 was in the sun, and then 5 were indoors, including an incandescent scene, an indoor daylight scene, a warm white LED, an RGB-based LED that was creating white light, along with the sodium vapor lamp that has kind of one distinct peak around 589 nanometers in its emission spectrum. Now, in order to display these within the somewhat limited dynamic range of a typical LED panel-based virtual production stage, we developed a light source dilation technique to reduce the dynamic range of HDRIs, which you can see the reference for here. It's going to be a poster at this year's SIGGRAPH, and you can see results for our scenes here as well. So we went out to take photographs of ourselves with our lighting reference spheres, our color chart, and our reference floral shirts, one of which I'm wearing at present while I'm recording this video. So here's us outside in this daylight scene in a park. And then here we are inside an RGB virtual production stage where we're using the standard kind of baseline calibration technique where we're calibrating the stage to just make the background pixels look correct. And here, what we're looking at in the scene, besides the 2 subjects and our colorful clothing, we're looking both at a color chart that's being illuminated inside the virtual production stage, as well as a color chart that's been composited into the in-camera background so that we can evaluate the color rendition there as well. And I'll flip between this image and the previous one, and you can see the color differences, particularly for Paul's shirt on the left. In the next stage of our process, we're going to now post-correct the shot with matrix Q. And now the idea is that the real color chart should match the original scene. And if I flip between this and the non-corrected version, you can see a large color difference. Now, next, we're going to inverse correct the background pixels with our matrix N, as in norm. And if I flip between this and the previous one, you can see the background changes slightly. And then finally, we're also going to apply a black level subtraction to the in-camera content behind the subjects because unfortunately the light that's falling on the actors, the subjects here, is also reflecting off the LED panels, which have substantial reflectivity themselves. And now I'm going to flip between this photo, which is kind of our full process, and the real outdoor photograph. And although we haven't matched the background perspective exactly, the color rendition is generally believable. And so to summarize now, we can look at the full process. So the original outdoor scene is in the upper left, and next you can see the baseline calibration approach if you just drive the LEDs to make the background pixels look correct. We see substantial color rendition errors here for the foreground subjects. Next, we can post-correct the full image with Q, which fixes some of those foreground color rendition issues. And then in the second row now, we can inverse correct the camera background with the matrix N as in norm, and then finally apply our black level subtraction. We do see here a dramatic effect that the new workflow has on the foreground color rendition, and also a large effect of the black level subtraction for the in-camera appearance. So here's another example for one of our other lighting environments with the original scene in the upper left, the baseline calibration approach in the middle of the top row, and then our full technique in the lower right with the intermediate steps in between. And although I'm not going to show all the results for the 7 different lighting environments, you can come to the DigiPro talk for that, I will show the result for the sodium vapor light because it really demonstrates the technique at its fullest. So here in the upper left corner again is the original scene. And you can see here that the unique spectrum of the sodium vapor light source makes the scene look almost monochromatic to our camera. Now when we drive the virtual production stage to try to make the background look correct, we see, yes, we largely can make the background colors match. However, an RGB LED virtual production stage that's trying its best to make yellow light is going to end up mixing together the red and the green LEDs, which are broader in spectrum than the original sodium vapor light. And so we now see colors emerging. You see that in the middle of the top row. Now our post-production technique here enables completely desaturating these colors towards the monochromatic look. But unfortunately in this case the post-correction matrix Q is poorly conditioned, and so we're actually unable to invert it to apply the inverse on the background. So we've seen at this point that we can ameliorate some of the color rendition challenges that come with using RGB LEDs. And so this begs the question, can we just use RGB LED panels after all that? And the answer we think is probably not. There are still color rendition errors that are visible on set to the eye. There are still color rendition errors in camera for certain colored materials, materials with specific reflectance spectra. It's also challenging to make bright light sources inside virtual production stages that have hard shadows. And it's also difficult to make spatially varying lighting. Also, cinematographers are often looking to intermix virtual production with broad spectrum studio lighting, which leads to its own unique set of difficulties. And then finally, the black level challenges due to panel reflectivity are a real problem that needs to be addressed. So on this note, I want to thank all of our collaborators over the years for their dedication. I want to thank the virtual audience for watching. I hope that we've all left today with an appreciation of the spectrum of lighting that we're going to be using to illuminate actors inside our virtual production stages. And cheers, and hopefully we have a lively conversation in the live roundtable version of this talk. Thank you.
Hi, I am Christophe Hery, lead of the Rendering and Material Appearance team in Meta Reality Labs research in Sausalito. Along with my colleague Carlos Aliaga, we will talk today about a different usage for spectral data in rendering, namely estimation of spectral biophysical skin properties from captured RGB albedo for digital humans. This presentation is based on our previous work, so you can refer to our paper for more detail. However, we also added some new results that you will see later in the course, exploiting deeper the spectral footprints of the skin components for the properties estimations. The image on the screen shows in a nutshell the main features of our pipeline, using one of our colleagues at the labs as an example. We take as input a captured RGB albedo and estimate the most important properties of skin that explain such albedo. The inset is the error scaled 4 times for better visualization. On the left, the captured versus the reconstructed albedo for the estimated properties, and below, 2 of the most important maps, melanin and hemoglobin. On the right, demonstration of robust editing of the skin components. We strive to fit existing production pipelines, employing state-of-the-art graphics rendering solutions. We get our input signals from a light stage dome capture. This device is currently the one that provides the highest level of fidelity in terms of geometric details, such as pores. Our goal is to perform robust estimations of skin diffuse properties. For clarity, specular reflectance of the skin is simulated using microfacet models when doing final renders of the 3D face, but this is not the focus of this talk. Also, the whole pipeline operates in texture space, as we will detail later on. For such purpose, we require to find a minimal parametrization of the skin, so that we can perform any kind of physically based edits in an easy and robust way. This parameter space also describes a physically based manifold of skin albedos that could be useful in inverse rendering contexts. So, once established our goals and requirements, let's do an overview of skin optics and what determines the appearance of skin. It is well known that skin cannot be treated as an homogeneous translucent volume, but as a complex material where each layer interacts with lights in a different way. Let's use this simplified scheme. From top to bottom, the main layers are stratum corneum, epidermis, dermis composed of two parts, and hypodermis. When a beam of light reaches the skin surface, only about 5% is reflected due to the change in the index of refraction. This is the white specular component of the reflected radiance. Then, light penetrates inside the tissue, where two types of events take place, scattering and absorption. After a number of these events, light is completely absorbed or goes out of the tissue again. This subsurface scattering component is what gives the color and translucent look to the skin, and is dependent on many factors, such as the structure and the chemical composition of each layer. The primary factor affecting the scattering are the collagen fibers. Other structures, such as keratins, have lesser impact. For absorption, the major chromophores are melanin, with two types, eumelanin and phenylanin, present in the epidermis. Hemoglobin, present in the blood in the dermis, which can be oxygenated or deoxygenated. Bilirubin, also present in the blood. Beta-carotene, which is an orange chromophore that depends mostly on diet and is present throughout the skin layers. And water, also included here since its absorption is negligible in the visible range but is significant in the infrared, for instance. Our goal is to explain the diffuse reflectance through the major components of the skin. Why is spectral needed? Reflectance spectra have been used to study skin's physical structure and chemical content, and reflectance spectroscopy is a widespread technique for obtaining dermal information. Spectroscopy is the study of the interaction of matter with electromagnetic radiation as a function of the frequency of the radiation. Measurements of skin reflectance are obtained by illuminating the sample using a light source with calibrated spectral power distribution and capturing with a multi-band digital imaging device, a spectrophotometer. The measured spectra can then be used to estimate the distribution of the skin chromophores. Chromophore estimation techniques are well known in tissue optics and medical imaging, and several commercial technologies have been developed, such as derma spectrometer, nexameter, chromameter, EMM01, SIScopy, TV, or many brands of over-the-counter fingertip oximeters that measure the oxygen saturation in blood. The main assumption from spectral spectroscopy is that each component in the tissue has a characteristic spectral signature that can be used to obtain its concentration from measurements. This is true for the main components of the skin, as shown in this log scale plot. The ordinate here is the spectral absorption coefficient of the major chromophores, that is the molar extension divided by the molar weight. In abscissa, we go from 200 nanometers to 1000 nanometers. As we can see, the spectral dependency is clear and becomes critical for faithfully reproducing any skin color. As shown on the left of this slide, recent measurements have demonstrated that skin scattering is a combination of Mie and Rayleigh scatterings. On the right, even the anisotropy of the phase function has been proven to be wavelength dependent. As light suffers scattering and absorption events inside the tissue, that spectral signature manifests itself on the aggregated emerging spectrally resolved reflectance in a strongly nonlinear manner. In these plots, the bulk concentrations of melanin on the left and hemoglobin on the right increase for each line, resulting in notorious changes on the spectral reflectance of the skin. The bottom color squares represent the RGB skin reflectance obtained as the concentration of melanin or hemoglobin increase. Note that such spectra are computing using our own 2D layering framework, as we will see later. This plot illustrates the effect of spectral resolution on the final simulated appearance from the chromophore spectral data for different skin types. Using a resolution of 10 nanometers, totaling 40 spectral bands, offers a good balance between error and computational time, showing similar results to 5x more spectral bands. We can also see that even with visually similar appearances in RGB, the spectral reflectance presents strong differences between different types of skin. For light skin, the spectral reflectance presents a characteristic W shape that progressively flattens as melanin concentration increases. On the other hand, dark skin presents a flatter spectral profile and lower amplitude, which might result on larger visual errors, even for small deviations on the parameters. This spectral footprint could be of enormous value for classifying the skin components more accurately. In summary, we have developed a method to manipulate albedo maps in a biophysically valid space. Using the results of a spectral Monte Carlo simulation, we project albedos back and forth to densities of skin properties, for instance melanin and hemoglobin. For example, you can see how increasing melanin content fivefold results in a darker skin albedo. So here is the proposed pipeline for reproducing skin colors. We start by pre-computing the final RGB colors resulting from various combinations of the skin layers content, spanning biomedical ranges. The chromophores within the skin tissues have known and measured spectral responses, which we eventually accumulate in a Monte Carlo random walk, then downsample back to RGB. By construction, these color tables will be biophysically motivated. Then, we learn the non-bijective mapping from RGB albedos to their corresponding skin properties, training a neural network with the dataset of pre-computed skin tones. From there, we can take RGB captured albedos and find the most probable combinations of skin properties. This eventually gives us the various concentrations of the skin chromophores. At this stage, we can edit or interpolate these components. Finally, we can render images under arbitrary lighting with a random walk subsurface scattering solution, more generally through physically based shading models.
Thanks, Christophe. Hi, I'm Carlos Aliaga, and I'm going to dive a bit in the details of our model and show several results for skin properties estimation, editing, and also the benefits of further exploiting the full reflectance spectra at certain stages of inversion. The goal here is to obtain measurable diffuse reflectance spectra as a result of the light interaction with the layer skin and its content, especially the chromophores. To compute this, we first tried other simplified models commonly used as Kubelka-Munk. However, we end up writing a small 2D spectral Monte Carlo random walk for better accuracy and to avoid assumptions. For instance, the relationship between the coefficients of Kubelka-Munk model and the radiative transfer theories are not entirely clear, despite there are a bunch of works in the optics community trying to find such relationship empirically. To compute the spectral reflectance of the skin, from a light source on top hitting the surface, we simulate the photon traveling along the cross-section using the radiative transfer theory in 2D. These example images are cross-sections of the skin computed by splatting millions of photons along their paths, at their scattering and absorption events. On the left, a skin with 5% concentration for both melanin and hemoglobin. On the center, another version with increased 15% blood. And the last one just shows how very high melanin concentration in the epidermis absorbs light in a more extreme way. In the previous slide, you could notice the model has only 2 layers. We performed several simplifications of the skin model, including a layer reduction, as well as a simplification of the layer interfaces. There are several reasons to do this. First, it avoids the need to model certain properties of the skin that are difficult or impossible to measure in reality, and have minimal effects in the reflectance after the many bounces light undergoes inside the skin, like the roughness of the inner interfaces. Second, it greatly reduces the simulation times, which becomes important after when we need to generate more than 500,000 samples to create a dataset used to learn the mapping. And finally, we aim to reduce the number of parameters defining the model to a minimum expressive set. This has two main benefits. First, the model remains practical so that the editing is still intuitive and not too cumbersome. And second, inverse rendering can find reasonable parameters, avoiding extreme metamerism, meaning that if many extra parameters were added, each with very subtle effects on the final reflectance, the parameter entangling would make probably the inverse problem intractable. In our model, we decided to reduce the number of layers from 5 to 2 main layers, epidermis and dermis. This assumption has been proven to be adequate in the past and fits our purpose of keeping the model simple. To build a 2-layers model, we simplified the epidermis by considering only the optical properties of the living epidermis, ignoring the stratum corneum. This is reasonable, since the stratum corneum has a minimal effect on the skin albedo due to the low chromophore concentration and small thickness, usually 5 to 20 microns, depending on the body location. The main effect, though, of the stratum corneum is on the specular component, which is out of the scope in this talk. The optical parameters of the dermis, on the other hand, are computed by weighted averaging the absorption and reduced scattering properties of the reticular and papillary dermis. We model it as a semi-infinite medium, omitting the subdermal layers that vary from a specimen and part of the body. For instance, adipose layers, muscles, cartilage. We empirically found that the finite dermal thickness has a minimal effect over the resulting skin albedo. Also note that this is next to impossible to infer the exact local shape of these interfaces in vivo, except maybe via expensive MRI scanning. Talking about the parameters influence, we realize that the epidermal thickness does really play an important role in the skin diffuse reflectance. This is something that has been frequently overlooked in the past, or just set to arbitrary values that could convey a reasonable final albedo. Moreover, it varies a lot depending on the body location, but even along different areas of the faces, as we can see in the image that depicts the relative thickness of the epidermis at different areas of the face. This is an example run with our model of how this matters. Both tables vary the concentration of melanin and hemoglobin at the same rate. From left to right, higher hemoglobin concentration, from bottom to top, higher melanin concentration. The only difference is the epidermal thickness, 60 microns versus 120 microns, and two extra parameters that turn out to be critical: the ratio of melanin types and the ratio of hemoglobin types. For melanins, the eumelanin versus pheomelanin ratio, where eumelanin is much darker and desaturated. For the blood oxygenation level, oxygenated hemoglobin is way more saturated in red hue than the deoxygenated hemoglobin, that leads to a more bluish color. These are such ratios in isolation, for oxygenated versus deoxygenated hemoglobin, and pheomelanin versus eumelanin on the right. Remember that this is enhanced even more by the epidermal thickness. Putting all together, this is the final list of parameters and their plausible ranges that we use to create our albedo space. The thickness of the whole epidermis is a parameter we vary from 10 microns to 350 microns. We allow thinner epidermis than the usual values of our normal skin to be able to handle lips nicely, as we will show later in the results. Also, for the remaining parameters, we allow the model to expand beyond what is plausible in regular skin, since we want the model to be robust to non-skin areas such as hair. These tables show increased melanin and hemoglobin as shown in the scheme on the right, showing the effect of different thickness for each row and different combinations of melanin type ratios and blood oxygenation levels. Some parameters included in the model, like bilirubin or beta-carotene concentrations, remain fixed to common values of human skin measurements found in literature. The remaining 5D parameter space is sampled as follows. Melanin and hemoglobin are respectively selected cubically and quartically, and this is done to better adjust to their nonlinear effect on the albedo, as we can see in these plots we showed previously. Epidermal thickness, melanin type ratio, and hemoglobin type ratio are treated uniformly. Of course, we aim for minimal skin parameterization, but expressive enough to handle most skin types. However, there are very bizarre and very uncommon skin types, as this example. You can read more about the blue people of Kentucky on the link. After analysis, it turns out that their skin color is due to excess levels in the blood of methemoglobin, a third kind of hemoglobin, apart from deoxyhemoglobin and oxyhemoglobin that we already consider. For our skin model to handle this added chromophore, all we need is the spectral response, which we found online. The skin palettes on the right veer towards blue with the concentration of this methemoglobin. Our biophysical model defines the forward mapping from the skin parameters to the skin albedo. For the inverse process, we need to characterize the mapping from the skin albedo back to the skin parameters. The non-bijective nature of such mapping, where many combinations of skin properties can lead to the same albedo, makes this task challenging. We found that this mapping, that operates per pixel, benefited from the inductive bias of the neural network that ultimately forced smoothness in the recovered maps, and thus enabling robust manipulation of the estimated properties. That means, for a particular albedo at a given pixel, the mapping returns the most probable combination of skin properties, and does so for the neighbors without abrupt discontinuities in the skin properties if the two albedos are close. Here we show two of the several tested options for learning the mapping. On the left, the network to map albedos in RGB to skin parameters and the reverse. On the right, exploiting spectral footprints in the decoder network to impose harder constraints in training. They share the same structure, an encoder-decoder with two fully connected layers of 70 neurons for RGB mappings and 256 for full spectrums. As we mentioned earlier, spectrums have 40 bands. The learning is fully supervised, and the dataset is composed of 600K samples, with 80% of it for training. We use quasi-Monte Carlo for a better coverage of the sampling space, and then applying the nonlinear mapping I mentioned a few slides ago, cubically and quartically for melanin and hemoglobin. If we focus on the losses for each case, both networks share the same skin parameter loss in the encoder E, defined as LP. It is simply the mean square error of the ground truth skin properties versus the estimated properties from the input albedo. However, the rest of the terms are different between network A and B. For network A, this is the RGB mapping. Both the decoder and the full cycle loss are the L1 loss of predicted versus ground truth RGB albedos. Instead, the network B employs the spectral albedos in different ways. The full cycle loss downsamples the spectrum to its corresponding RGB and compares against the RGB albedo ground truth. The decoder D compares directly the predicted spectra against the ground truth spectral albedo through SAM, or spectral angle mapper. SAM is a distance metric that measures the similarity of two given spectra, basically measuring the angle between two n-dimensional vectors. It is a well-known metric often used in spectral sensing problems. For example, spectral unmixing, where a given spectrum is interpreted as an aggregation of several n members, that is, materials with known spectral footprints. It has the advantage of being agnostic to the amplitude, thus only focuses on the spectral curve, that is, the hue or the skin tone in our case. In our test, imposing such constraint only in the decoder part of the network consistently reduced the reconstruction errors, as I will show next. Before jumping into the results, I want to clarify some technicalities of the framework. The albedo space is generated through spectral computations, but input albedos are in RGB space. To downsample the multi-band spectral values into RGB, we use an existing integration approach, although we could rely on other concurrent works to this end as well. Most color spaces will work here. We use sRGB, considering that diffuse albedos have a rather limited gamut and dynamic ranges, as we can see in the input albedos used for validation later on. Also, for all the results shown in the talk, we use D65 illuminant, since that was the power spectra for our captures. However, we can plug in any new illuminant by just retraining the mapping, using the spectral dataset and downsampling the spectrums to RGB with the right illuminant. Also, the final 3D lead geometries of our virtual faces are rendered using our own skin materials inside Blender Cycles community. For the diffuse component, which is the focus of this course, we use a 3D random walk source of phase scattering solution that relies on numerical albedo inversion around the mean free path and accounting for the anisotropy factor G. The model is single layer at this point, with dermis and epidermis combined as a semi-infinite medium. Multi-layer models could be employed, for instance directly consuming the chromophores estimations, but these are out of the scope of this course. And now, going through the results, we perform estimations of skin parameters over several skin types covering the Fitzpatrick's scale. The columns here show 5 different subjects that were captured using LightStage. It's important to note that some captures were done by ICT and some others were done by ASCO, a company located in France, so this was a good way to test the robustness of the model. The original captures are then in the first row, and the second row shows the reconstructed albedos using the RGB network and the spectral decoder network. The insets show the absolute error scaled by 4 for visualization purposes. The most interesting insight of the RGB versus spectral is the improved recovery of the original skin tones, with less shifts in the hue through the spectral mode. This points spectral metrics and the spectral angle mapper loss as the right directions for more robustness. For instance, look at non-skin areas, like the hair of the first subject, where the spectral decoder network does a much better job preserving the hue of the hair, or the bird and the t-shirt of the second subject, where again the original hue is better preserved in the spectral solution. And these are the corresponding estimated parameters resulting from the evaluation of the RGB network in the first row and the spectral network on the second row for all the subjects, which are sorted by skin type from light to dark, and we can see the progressive increase in melanin content is coherent with the skin type, and how both spectral and RGB networks stay in similar ranges. Just picking one example of the lightest skin to have a closer look, note how melanin spots are nicely isolated from small capillaries, veins, or reddish imperfections. Also, the color of the lips is mostly due to the high concentration of blood and the relatively thin epidermis in all cases. These are some results of editing all the parameters included in the model. We use a very diffuse and flat illumination to better appreciate the subtle changes in skin appearance. This is the rendering using the original albedo, and this is the first editing result of modifying the level of blood oxygenation that translates into a paler skin color when deoxygenated and a more saturated look when oxygenated. Note how not only the overall skin tone changes, but also the capillary veins, for instance in the eye bags, or some of the heterogeneities on the forehead change in a realistic way. Here we show the thinning of the epidermis, which typically occurs with aging, and translates into a more translucent look, revealing the heterogeneities of the underlying layers, for example the capillaries and veins. Instead, a thicker epidermis results in a more opaque and rough appearance. Last, we vary several components to simulate tanning and flashing. We got a bit more playful with the skin properties editing and did this test where we have areas of the face that completely lack melanin, as happens in conditions like vitiligo. We further validated the editing capabilities through 3D renderers and their different illuminations for all the subjects with different skin types. Please check the course notes to see the images at higher resolution and appreciate the details. In conclusion, we have presented a solution we employ at Meta to recover and robustly manipulate the biophysical properties of human skin from RGB albedo captures. Spectral simulations are crucial to accurately reproduce the skin colors. Lifting from RGB to spectrum is not only needed for accurately computing the diffuse albedo of the skin, but it can be useful at different stages of the inversion framework for better constraining the optimization space. It leads to better preservation of the original skin tones while still estimating meaningful skin properties. In the short-term feature, we want to include variations of other extra chromophores that change more temporally, like the beta-carotene, bilirubin, or any other dietary or health-related conditions. And we also want to further validate the current method with hyperspectral captures in an end-to-end spectrum to skin properties to spectrum learn mapping. And this is all for this talk.
Hello and welcome to Chapter 4 of this year's Spectral Rendering course at SIGGRAPH 2022. My name is Jean-Marie Aubry. I'm a senior researcher at Wētā Digital, also known as Unity New Zealand. At Wētā Digital, we developed and maintain Manuka, which is a spectral renderer used for all the feature film production of Weta FX, which is our sister company. I will be presenting the first part of this chapter, and my colleague Kirk will present the second part on resampling. Okay, so first, a brief overview of what we are talking about. In spectral rendering, we are simulating the response of a camera sensor, that is the R, G, and B component of a pixel, to incoming light. The model for this is an integral over the sensor area, X, over the incoming angular domain, omega, and over the wavelength domain, lambda. At the integrand, we have a product of L, which is the incoming radiance, and Rho, which is the camera response, or the sensor response. Now, the sensor response would be an R, G, and B, so a three-dimensional vector. However, for the purpose of noise analysis, it is well known that it is the luminance that the human visual system perceives more in terms of noise. And that the color noise is kind of secondary. Moreover, we have a very good denoiser that deals with color noise quite efficiently. And so for these reasons, instead of analyzing the convergence of R, G, and B, we are going to analyze the convergence of the luminance. In terms of this integral, this means that we will replace the R, G, and B response curves by a luminance response curve for the camera. And this has the great advantage of having to compute the variance of a scalar variable. So we have this integral, and numerically, the best way to compute it is to do a quasi-Monte Carlo integration. Now for this course, we're going to focus exclusively on the integration in the spectral domain. We will come back to sampling of the path a bit later. So this integral, now written as such, I equals integral over lambda, the spectral domain, of luminance sensitivity at lambda times incoming radiance L. And we estimate this integral by random sampling a wavelength lambda and using this estimator, so values of response curves times luminance at this random lambda, divided by the PDF of the distribution that has been used to sample lambda. On the chapter of Monte Carlo or quasi-Monte Carlo, the difference is, of course, that in quasi-Monte Carlo, we use a stratified sequence of random samples instead of using purely random samples in normal Monte Carlo. And that has the advantage of of making convergence much faster. It complicates the analysis a little bit, but if we write just the one sample estimator, then whether this sample came from Monte Carlo or quasi-Monte Carlo, it doesn't matter. It matters only when we combine many of the samples in one multi-sample estimator. So if we focus on the one sample estimator, then we have to sample a variable lambda and plug it into this expression to get an estimator. So of course, there is a latitude in choosing this PDFP. The only hard constraint on it is that it should vanish, so be equal to 0 only where this product is equal to 0. And that's the only condition, so that this estimator is an unbiased estimator of the integral I. So choosing a PDF for lambda that gives you a good estimation of your integral is known as importance sampling. It is well known that when the integrand is non-negative, then the best possible choice for the PDFP would be that integrand. So the product of rho and L normalized so that its integral becomes equal to 1. And of course, if you have that, then you have solved the problem of computing the integral. But still, that is the goal, and that is the ideal for importance sampling. However, in our particular situation, we need to consider a case where the integrand can change sign. And that's a little bit surprising, considering the quantities that we are integrating. But it is a byproduct of the way the luminance response curve has been estimated to match a given physical camera, because camera manufacturers only publish RG and B response curves because they are RG and B sensors. But the luminance must be deduced from a best fit, comparing it to the known luminance of square on the MAC-based chart. This is a little bit beyond the scope of this course, but let us just deal with the fact that rho may be changing sign. It may be negative in some small areas of wavelength, typically in the blues. That this integrand may be changing sign, and that it is therefore not suitable to make a PDF. But the answer is not very different. You just have to take the absolute value. So instead of taking rho of lambda, L of lambda, you take the absolute value of them and you normalize again by its own integral, so that the integral of P is equal to 1 and P is a PDF. And this is where I managed to sneak in a little bit of mathematics. The proof that taking the absolute values and normalizing gives you the optimal PDF for the Monte Carlo estimation of integral of a function G, say, is quite simple and instructive. So first, we can compute the variance of that estimator, so the Monte Carlo estimator that would use P0 of X, and find out that it is simply the difference between the integral with the absolute value n squared and the integral without the absolute value n squared. And you can see, of course, that if G was non-negative, or indeed never changing sign, then this optimal variance, oh, sorry, I'm saying optimal, I still don't know if it's optimal, but this variance of this particular estimator would be 0. And if there is a change of sign, it will be strictly positive. It's a necessary and sufficient condition. And then if we consider any other PDFP, which may be different from P0, then there is a neat trick. I will refer you to the course notes if you can guess, to use the Cauchy-Schwarz inequality and establish this inequality. And this inequality, if you subtract this term on both sides, you obtain that the variance of estimator using P0 is always smaller or equal to the variance of any other estimator. And this proves the optimality. Okay, so the optimal PDF is not known directly. It needs to be estimated. So, well, typically, part of this product will be known. If we are doing path tracing, so we're starting an array from the camera, then we know the camera response of that particular pixel, but we don't know until we sample it the value of the incoming luminance. And conversely, if we were light tracing, so starting from a light, then L would be known as the emission, but not the camera response, because in this term of camera response, we actually need to propagate what is known as the importance from the sensor down the path to the light. So L is known, but rho is not known in the case of light tracing. So anyway, the problem of finding the missing information is a problem of non-parametric estimation. We are trying to find out what the missing function is. And this is not an easy problem to solve, but a very good starting point is this paper of Van der Wit and Eisenman called a multipath method for accelerated spectral sampling, which we followed to basically do a bilaterally filtered histogram estimation of the desired PDF. Okay, now the picture gets a little bit more complicated with the introduction of multi-wavelength sampling, also known as the Hery wavelength sampling technique, after the paper of Wilkie and his collaborator of 2014. Wavelengths are typically sampled by packets of 4, 4 being the width in float of the SSE lane in current hardware. And thanks to this, not only do we get 4 samples essentially for the price of 1, but also we can impose a nice stratification between these four samples. Importantly, the sampling of the path may depend only on one of these wavelengths. And canonically, we will use the first one, lambda 0, as a parameter for sampling the path. And this becomes known as the Hery wavelength. And the 3 remaining wavelengths, lambda 1, lambda 2, lambda 3, are 3 different deterministic functions of the Hery wavelengths. And what you put in this these shift functions will govern the spread of the other wavelengths. And this is where the stratification properties comes from. And stratification in this case means that color noise will be greatly reduced. So we don't want to lose that. So in the literature, there are mostly two ways of spacing the other wavelengths from the Hery wavelengths. In the original paper of Wilkie, the shifts were uniform in wavelength. So if L were the length of the wavelength domain, which is about 340 nanometers, and that's roughly 0.00193 TWIPS if you live in the UK, then lambda 1 will be lambda 0 are Hery wavelengths plus L over 4. Lambda 2 will be lambda 0 plus 2 L over 4, and so on. So that is uniform spreading in wavelengths. Another possibility is to spread the wavelengths, so the probability between them, which in this illustration would be the area under the curves between two of those black lines, is constant and equal to 1/4. And the formula for this is to use this shift function, which is defined using the cumulative distribution function associated to this PDFP. Yeah, like I was saying, that's a natural idea, and it has come up independently in several places. And I think it is mentioned for the first time in the continuous multiple importance sampling paper of West and collaborators in 2020. So we call this equiprobable spacing, and then this choice of a shift function has some interesting consequences. First of all, the induced PDF of the non-Hery wavelengths are exactly the same, and by this I mean not the shifted ones, as that of the Hery wavelengths. So these two functions, P, which is P0, and Pk are equal as functions. And that is in contrast with uniform shifting, for which the PDF of the shifted wavelengths would be the shifted PDF of the Hery wavelengths. And then after some calculation, for which I'm going to refer you to the course notes, we can compute the MIS weight, so the multiple importance sampling weight, in the case, with which we want to balance the 4 samples that have followed our path. Okay, so we have 1 Hery wavelength and 3 others, which form the lambda k, and each of those gives us a contribution to the luminance. And we average them using those weights. And this is the classical formula for the balance heuristic MIS weights. And after some computation, this simplifies to something that is, something that is very neat, which is this expression, which you can notice that they don't depend on K. So that's interesting. All 4 wavelength contributions have the same weight. They will depend from sample to sample, however. One thing worth noting in this formula, we have the conditional probability of the path with respect to the Hery wavelength, because that's how that path has been sampled. It has been sampled knowing the Hery wavelength. But we have also conditional probabilities for the same path, but as if it were built on a different wavelength than the Hery wavelength. we can go all the way and mix multiple path sampling techniques, which can each of them have their own wavelength sampling PDF. And in that case, for each of those path techniques, L, the hero wavelength, which now depends on L, drives the sampling of path number L, and also through its own shifting function, it drives the value of the other wavelength lambda LK. And okay, here is the final formula. I'll again refer you to the course notes for these developments. And I think I might conclude here with this pretty picture. And a few remarks. So the first thing, I mentioned that the stratification in wavelength is crucial in reducing the noise. But of course, it complicates the convergence analysis and the computation of the variance, because in this case, the variance starts involving cross products of the integrand for all possible pairs of wavelengths. So it gets trickier. As a result, when sampling a single wavelength, you see huge gains from going from a uniform distribution to a non-uniform distribution, something that is tailored to the characteristics of the picture. So that's the whole spectral guiding part. And then the gain is about 30%, so 30% faster convergence in single wavelength case. But because of this stratification complication, the gain in multi-wavelength is a bit less, about 5%. So yeah, that's interesting. And finally, the choice of those equiprobable shifts, it is nice. It simplifies the computations incredibly, but it remains arbitrary, and I'm not 100% convinced that it is optimal. So maybe there is room for discussion here. If anyone knows, please contact me at Jean-Marie Aubry at unity3d.com. And I will thank you for your attention. And please get in touch with me if you have any questions.
Hi, my name is Jirí Vorba. I'm Senior Rendering Researcher at Unity Wētā Digital. I'm going to continue with the second part of our chapter named Sampling and Resampling in Spectral Rendering. In this part, I'm going to talk about our experimental integration of resampling within our spectral renderer. Resampling has been brought into the context of computer graphics by Talbot and colleagues already in 2005. Recently, resampling get attention by the research community thanks to the work of Bitterly and colleagues when they introduced the so-called RESTER algorithm, spatio-temporal reservoir resampling, in the context of real-time ray tracing. Another work that we heavily built on is the generalized resampled importance sampling that is being presented in this year's SIGGRAPH by Lin and Kettunen and colleagues. And this work is mostly important for us because it provides a great generalized theory, and we try to stick with our notation so that we comply with their framework. So what hasn't been studied in great detail in the previous works is the spectral part. That is how we can integrate the resampling so that it works well with the hero wavelength sampling that Jean-Marie talked about in the previous chapter. This is the focus of our work. Same as Bitterly and colleagues, we study the resampling at the problem of direct illumination calculation. So we trace a path through a pixel, we determine the primary vertex, we call that vertex Z, that is a receiver of our illumination, and we want to compute the reflected radiance O towards the camera from that point. To that end, we need to integrate over the emissive points ZE and compute the product of the BRDF, emitted radiance, G-term, and the transmittance. What is missing in the previous equation is the fact that we also integrate over the spectral domain. That is, for each pixel, we want to evaluate this integral, which is integral over the product of camera response R and the reflected radiance. We denote this simply as F, that is the contribution that we want to continue to compute for each path. And to do that, we first start with a sampling of the hero wavelengths lambda 0, which gives us another 3 wavelengths that we evaluate for the same path. This is the same as Jean-Marie talked about in the previous chapter. And when we arrive at the receiver vertex, we generate 2 sets of samples. One set is simply unidirectional samples that we get from the collision of rays with light sources. This is what we all know as unidirectional path tracer. And the second set of samples are next event estimation samples ZE and EE that are given by the resampling process. Now this yields 2 different estimators. One, A, is an estimator that is defined in the good old Monte Carlo way. That is, we have the contribution F divided by the probability of generating that sample P. Whereas in the second case, with the resampled next event estimation points, we have an estimator in the form of contribution F multiplied by the unbiased contribution weight W. And also thanks to the generalized resampled importance sampling and the previous works, we are able to combine these two through multiple importance sampling. I should say at this point that previous works usually work only with the second estimator, with the unbiased contribution weights. That is, they use other sampling techniques, like for example the unidirectional sampling, only to provide a candidate samples into the resampling process. So the multiple importance sampling weights used in those works are inside that estimator, whereas here we have like 2 estimators and we want to combine them only after the resampling has been done. So now let's look at how we generate those resampled next event estimation points. We use 3 steps, similarly as in previous work. That is, in the first step we generate some fresh samples, which we will then merge into the current so-called reservoir that is associated with the pixel through which we trace the path. And in that reservoir, we store samples from previous progressions. So that is the second temporal resampling step, but unlike in previous work, where the samples were taken from the previous frames, we actually reuse samples within the rendering of one static frame. We do this because usually in the offline rendering, this is our context. In the offline rendering, we use hundreds of samples to converge the image, and we progress in iterations. So we reuse samples over these progressions, and the third step is that we also look at the neighboring pixels, at their reservoirs, and we reuse the information in them so that we merge these reservoirs into the current reservoir given by the current receiver vertex. So let's look at these steps in the detail. So first we generate fresh samples, that is, we generate some candidate samples X, and we generate them with uniform probability. And for the resampling, we need to determine the risk weights for each of the candidate. And the risk weight looks as a ratio of the target PDF p hat divided by an actual PDF of the resampling. I should say that the p hat doesn't need to be PDF. It's just a general function. Usually, we will look at how we define this function later on. What I want to stress is that after this process, we end up with a point yi that has been resampled on the light. And the index I here refers to the current sampling techniques. This will be important for us later on. Now let's look at how we compute the target function p hat. We simply compute it as a product of the emitted radiance LE and the G term. Note that with respect to wavelength, we use the hero wavelength lambda 0 to evaluate the target function. And the resampling weight here is scalar, dependent on this wavelength. Now, for the temporal resampling, we take the fresh sample yi as an input sample, and we look what we have stored in the current reservoir from the previous iterations. That would be the sample yj. And to be able to resample yj and yi, that is, now these are our two proposals, we need to determine risk weights for each of them. So the risk weight for yi is the product of so-called resampling MIS weight m, the target function p hat, and an unbiased contribution weight w for that given sample yi. Note that again we evaluate the p hat function at the hero wavelength lambda 0, but this time we use the subscript I to depict that it is a hero wavelength that is used in the current iteration for generating the sample yi. The unbiased contribution weight w is computed as a fraction of the sum of risk weights used for resampling the sample yi and the target function evaluated at the hero wavelength. To define the risk weight of the previous sample yj, we need to acknowledge the fact that yj was sampled using another receiver point, zj, that was used in the previous iteration, together with a different hero wavelength, lambda 0j, that was also used for sampling that previous path. This is acknowledged through the existence of shift mapping from j to I, ti, and when we use this mapping, we also need to multiply the risk weight by the Jacobian of this mapping ti. Note that the wavelength is part of this Jacobian. However, in our experimental implementation, we set the part that corresponds to the change of wavelength from the previous hero wavelength lambda j to the current hero wavelength lambda I. We set it to 1. It doesn't seem to yield any problems, but we would like to investigate this deeper to know how we should set it properly. So to make it clear, this term means that we evaluate the target function with respect to the yj and zi, and also the current Hery wavelength lambda I, because we want to bring the sample into the current sampling domain with respect to the current technique I. Now let's look in the detail how the resampling MIS weight looks like. So for the sample yi, it is relatively straightforward. We use the target function with respect to yi, zi, and the current Hery wavelength sampling yi. But what is interesting is this term, that we need to know what would be the target function if we evaluate yi at the previous vertex zj. So again, we need to store some auxiliary data with each reservoir so that we can evaluate these quantities. So this involves the previous point zj. We also need to store the previous normal. We also need to store the wavelength, the Hery wavelength that we used to compute the previous iteration through that given pixel. For the yj, the resampling MIS weight is very similar, but this time this term is evaluated at point yj and the current receiver point zi, and also we should multiply it by the Jacobian of the mapping ti. Now for the spatial resampling, we actually can use the formulas exactly as we have introduced them for the previous temporal resampling step, only now we take some neighboring pixels as a reservoir that will be used for merging. So in these reservoirs we have our receiver points zj and samples on the light yj. So now we have we went through the points 1 and 2, that is, we sampled the Hery wavelength, we generate two sets of samples, we looked in the detail how to generate the resampled next event estimation samples at E and EE, and now we want to combine both samples, the unidirectional samples and the resampled next event estimation samples through MIS. To that end, we define the MIS weights W. The weights will be a little bit different for each of the sampling techniques. That is, we have weights for unidirectional sampling and we have weights for next event estimation sampling. So first, let's look how the MIS weights looks for next event estimation case. And also, to simplify it even a bit more, let's assume that we have no unidirectional samples at all. This may sound strange, but yes, even if we didn't have any unidirectional samples, we need to acknowledge the fact that we trace multiple wavelengths over the same path. So the subscript, the superscript k now stands here for the different wavelength sampling technique, and actually this formula has been already shown by Jean-Marie in the previous part of the course, so this is nothing new. The x here stands for the full path. We need to open the term px to evaluate this quantity, and this term is equal to the probability of sampling the path up to the point zi and to the probability with which we have generated the emissive points at E and EE at the given wavelength lambda k. Unfortunately, this probability is untractable. We don't know it because it is the probability that comes from the resampling process. But as it was suggested in previous works, we know that the unbiased contribution weight actually converges to the reciprocal of this unknown PDF, and we can use this fact to approximate our MIS weight. So to approximate this PDF, we multiply the unbiased contribution weight by the ratio of the target functions once we evaluate it with respect to the current Hero wavelength lambda 0I divided by the target function evaluated at the given wavelength lambda k. This can simplify to the ratio of the target function at lambda k divided by the sum of risk weights that are stored with the current reservoir that is determined by the receiver point Zi. Now we can generalize this so that we have multiple important sampling weights that takes into account also other sampling techniques. And to that end, we use the script L, which stands for the sampling techniques, and K again goes over the wavelength sampling techniques. This is again what has been shown by Jean-Marie, and we can easily evaluate the term Px uni. There are known probabilities. The only trouble we would have is again the Px and EE term, but this is very straightforward because we follow the recipe from the previous slides. So we open up this term and we arrive at this, say, generalized approximation of the PDF of generating the samples at EL. That is, if we are given the unidirectional, if we generated the emissive point ZE by a unidirectional sampling, and we want to know the probability of sampling this with respect to next event estimation, we just need to evaluate the target function for that point with respect to the desired wavelength lambda LK. Now I would have a few comments to this. We need to realize that from the practical point of view, it is necessary to realize that such an MIS weight is stochastic, and this comes from the fact that we divide by the sum of the risk weights. And in early progressions, this can be quite noisy, and in fact, it can even happen that we don't have any next event estimation sample that would be valid, and this sum of risk weights can be zero. In that case, the PT uni technique would get all the weight, and the high variance can project into our image. However, it may be just because of the variance in our PDF approximation, because in next iterations, when we already have some NE samples, these PT uni samples would be downweighted. So one should consider some warm-up progressions before we start taking the PT uni samples into account. Another interesting fact is that such an MIS weight helps us to arrive at the correct result, because they if these target functions are zero, that means that such a technique cannot generate the sample, and thus the weight needs to be distributed across other sampling techniques. Otherwise, we would be getting bias in the image. This is not surprising from the point of view of the Jiry's theory, although it might be tricky for people used to hero wavelength sampling, because one would, for example, set the MIS weight to be constant so that we ensure that it sums to 1 over all techniques. However, this would yield incorrect result in general. So now let's look at some results. We have experimented with one area light source which has a texture. This is an HDR matte texture, so in fact this area light source is many light sources next to each other. So in the right frame we had used uniform sampling, and in the right frame we used our experimental spectral implementation of Riester algorithm. We can see that it yields better results than simple uniform sampling in the left, which is expected, and also it converges to the same result, which experimentally prove that our formulas are usable. We have another case here. We have focused area lights, and for the equal time, it doesn't provide us a big advantage, but again, it shows that we don't have any issues coming from the fact that we combined resampling with hero wavelength sampling. At the end of my talk, I will stress once again that this is just work in progress, and it's an experimental prototype that helps us answer questions, primarily whether we are even able to use resampling algorithms together with our hero wavelength sampling that is vital for our spectral renderer. This seems that the answer is yes. We have figured out some practical details that we share with you in our course, and we hope that we will get to evaluating this technique in the production renders. So that's all from me. Thank you for your attention and enjoy the rest of the conference.
Hello everybody. My name is Daniele Siragusano. I'm image engineer at Filmlight, and I'm writing this lecture and giving this lecture together with my colleague Richard Kirk, who is scientist at Filmlight. Today, we want to discuss how we use spectral data and spectral calculation today, even within an RGB pipeline, meaning that we get digital RGB input from digital cameras, and we need to deliver RGB deliverables going to an RGB display. The techniques we are describing in the following are no theoretical exercise, but they form the basis of looks and transforms which are used over years on a daily basis around the globe within our products. The idea is quite simple. Let's use spectral calculation to derive an RGB to RGB transform. This fits quite well with traditional motion picture workflows. From now on, I will, when we're talking about this RGB to RGB transform derived from a spectral intermediate calculation, we will call this the spectral intermediate transform. The first step is we need to allocate a reference spectrum to each RGB input color. That is basically building our reference scene or our proxy scene. Probably the spectral composition of the original scene might differ a lot compared to or to the reference scene, but maybe it's close enough for certain use cases. In this figure, we show four different reference scenes commonly used in the industry also for other tasks like camera characterization and such. That spectral reference scene follows two spectral calculation pipelines which are set up indeed identically. We call this the input pipeline and the output pipeline. Here's just one of the two pipelines. We got the reference scene, and we got the light source and a spectral filter and an observer for each pipeline. Then we multiply the reference scene with the light and the filter and the observer respectively. This operation produces an RGB tuple, just a point here, for each spectral sample in the reference scene. Because we calculate two pipelines, we will have two sets of RGB tuples. If both pipelines would be identical, both sets of RGB tuples would be identical too. The input pipeline should model as close as possible the actual pipeline we want to, the actual input of our data. The output pipeline describes the desired output. Now, if we start to modify one of the two, a single property in one of the two pipelines, then we get two different sets of RGB tuples. And that difference is what this is all about. We will use these two sets of RGB samples to generate our nonlinear spectral transformation. Again, an overview of that pipeline here. Everything in blue is calculated or actually performed in spectral domain. This one is real light transport, and that is the spectral calculation. So we have the original scene, original light source, original filter and camera, and some camera processing, and when we get basically RGB here on the input. Now we take our reference scene, and now on that side should match as close as possible the original state. And that pipeline, our desired output. We generate again RGB outputs here, and these form the spectral intermediate transform. That we apply to the input data, and then we get our output data. Quite simple. Before applying the transform to an image, our image needs to meet a few criteria. Modern cameras can record scene-referred data if the dark levels are set up correctly and no nonlinear transformation has been applied. The camera RGB values should correspond to the light levels hitting the camera sensor. This image state is crucial to marriage the spectral calculation and the image data. The spectral calculation is applied in scene linear domain. Professional cinema cameras often apply per channel pseudo-logarithmic encoding, which we must undo before applying the spectral intermediate transform. And usually cameras white balance the picture by gaining the RGB channels. We can model this in our spectral pipeline as a chromatic adaptation transform of the observer. However, often additional chromatic adaptation transforms are applied to camera data. Some camera manufacturers use color temperature-based correction matrices so the RGB signal looks right on a monitor with a D65 white point. Additional matrices might be applied when an image is imported into a color management workflow with a different reference scene. And these concatenation of matrices are challenging to undo or to re-simulate. Remember, we need to model the input state of the RGB data as close as possible to produce a realistic end result. And we would love to have an exact information about the spectral sensitivity of the camera in use. But in practice, the camera spectral sensitivities are rarely known, hard to measure, and will depend on the lenses and filters in use. We have characterized, for this experiment, I'm going to show you the lighting, the camera sensitivities, and the RGB processing pipeline for the experiments as best as we could. So we were more careful than the motion picture industry usually is. Let's go back to the reference scene again. The quality of the transform will depend on the choice of spectra in our reference scene. We would like a spectrum for each object the camera sees, but this is not realistic and must settle for less. In professional motion picture pipelines, robustness is a critical property. What does robustness actually mean? Well, it doesn't break the image. And in our experience, a smooth transform typically is also a robust transform. Another valuable property we'd like to achieve in our spectral intermediate pipeline is exposure invariance. This means that the transform does the same thing to chromaticity values independent of their exposure. Exposure invariance transforms simplify the fitting process. Further, They allow us to cover an unbounded dynamic range, which is vital for dealing with scene-referred image data. It imposes a useful limitation also on the reference scene. Our reference scene can only have a single sample for each chromaticity. We also want to cover the whole spectral locus so that for each possible color value, a spectra in our spectral scene is close. If there are large missing regions in our color gamut, then the interpolation may not be accurate. This brings us to a new proposed set of spectra, the smooth spectra. It should be realistic. The spectra should be like real objects. It should be unique, one sample per chromaticity, smooth, similar colors, should have similar spectra, and it should have no gaps. If we look back at the collection of spectra, we can see some common patterns. There are some smooth peaks, round edges, and flat regions. So instead of measuring lots of colors, can we generate a set of spectra with the same properties? Let's try. There's a promising solution. For each color, as measured by a camera or a human vision, XYZ or LMS, we can solve for the smoothest spectrum. The one that fits our measurements, but also has the smallest sum of differences between adjacent wavebands. We do this via constraint optimization using Lagrange multipliers. This is a standard technique, and I'm not going to go through the mathematical details. But we will want to give you a worked example. We start with the magenta patch on a small X-right color checker chart. We measure the XYZ values for this patch. So we got 0.311, 0.197, and 0.284. Now what we do, what we're going to do is we're calculating in this example the reflected spectrum with 7 bands from 400 to 700 nanometers in 50 nanometer steps. A typical interpolation might have 201 bands going in 2 nanometer steps. So we calculate the XYZ weights of the illuminant for each of these wavebands. We multiply the 1931 weights by the illuminant light levels. The XYZ weights are the non-zero weights in the last 3 columns and last 3 rows. The red line shows the 550 nanometer values we have listed earlier. Multiplying the last 3 rows by the columns of the reflectant would give us the XYZ values for the magenta patch down here. The lines -1, 1, 2, -1, 2, 1 weights, these weights should get the reflectance values for 400 to 700 as close to the average values on either side without disturbing the XYZ totals. There are 2 extra rows, the 350 and 750 nanometer. These wavelengths have no weight, so they do not affect the XYZ sum. These rows should make the spectrum smooth at either end. We want to solve for 400 to 700. We do this by inverting the matrix. If we use a 2 nanometer interval, we would invert a 201 by 201 matrix. However, there are lots of zeros, so the inversion is usually quick and stable. The epsilon value is very small, typically is 10 to the power of -6. If epsilon is 0, the matrix cannot be inverted, so we usually use slightly different weights. But the results are almost the same. Then we ignore 350, 750, Rx, Ry, and Rz. The figure shows the reflectance spectrum for our magenta patch. The first line shows the actual patch as measured by the spectrometer. The graph is noisy a little bit on the left because the light source had too little short wavelengths, light maybe. The smooth spectra does not match particularly well, but that is not surprising. We were lucky that these values are all between 0 and 1, but there is nothing in the calculation that forces this to be so. Suppose the 550 nanometer value had come out negative. We return to the matrix and replace the 550 line with one that forces R550 to 0. We replace the diagonal value with 1 and replace the other highlighted values with 0. Now we repeat all of those steps for any chromaticity within the spectral locus to generate the complete set. Here we show the 4 standard data sets. used in the industry and the smooth spectra in comparison. And we can see that it satisfies all of the requirements we made earlier, obviously. So what do we do with that? We can change the illuminant, for example. But before we do that, we need to first look at chromatic adaptation again. In professional motion picture photography, the illuminant is chosen with great care. The director of photography will most often choose the illuminant which produces the intended look for a particular show. Normally this involves a lot of experience and test shoots before principal photography. A normal chromatic adaptation transform performed in the camera or in post should therefore not change the characteristics of the illuminant. We can clearly demonstrate this. Let's do this. We go full screen. What we've done is we've shot a exposure bracketing. Sorry, not exposure bracketing. We shot a color temperature bracketing here. So we used a light source, a LED light source, which with tunable lights, and we went from 2800 Kelvin all the way to 10,000 Kelvin. And we didn't compensate in the camera yet. So the camera was standard on RGB gains equal. And then what we also did is we shot with only the white LEDs in the light fixture, and then we shot with only the RGB LEDs in the light fixture. And we can see that we got a different color cast. Sorry. Now, if we do a standard chromatic adaptation transform, let's do this quickly. So I select all of the shots, add a base grade, pick a gray reference and hit match. And now what I'm basically selecting that region in the area where we have that unselective object. And what it will do is it will perform a standard chromatic adaptation transform. Quite a few shots. Okay. So if you go from 2800 slowly to 10,000, we can see that the chromatic adaptation transform is quite smooth. I mean, we would expect that because we only have a few degrees of freedom in that light fixture. We have maybe 5 or 6, I don't know exactly how many, but we have only a few LED light sources, and the color temperature is made from the same source spectra. But still, if we go from this 10,000 to white only, we can see quite a different rendering. And even if we go from 10,000, and let me do, yeah. If we switch directly from 2,800 to 10,000, we can get quite a dramatic effect here. So we can see here the blues are rendered very differently than here, right? And obviously if we go to the RGB only, then we get a completely different result. Most of the selective colors are much, much brighter and also much more colorful. So that is the look, basically, that the illuminant imposes onto a set. Let's go full screen again. As we demonstrated, the illuminant is a powerful tool in our toolbox, or in the toolbox of the director of photography. In professional motion picture pipelines, we expect that the look of the illuminant is carefully chosen and carries the vision of the director of photography. But sometimes, though, there are exceptions to the conservation of the illuminant look. Sometimes it would be desirable to shoot with a certain illuminant from a practical standpoint, while desiring the look of another one. Maybe it's more practical to use a certain light source because of power consumptions or other features, while still preferring the look of an unpractical or energy-consuming light source. For example, shooting LED lights, but actually preferring the look of a tungsten light source. Another example would be simulating exotic or even a little bit dangerous light sources. Extremely spiky illuminants, for example, like high-pressure sodium lights, can produce unpredictable results on many digital cameras. It would be safe to shoot an image with a broader light source and later in post-production apply a spectral intermediate transform to mimic the look, for example, of high-pressure sodium lights. Let's have a look at that. Again, we have these two pipelines. We use the smooth spectra on both, and then we use a broad light source, maybe daylight, no filter for this in this case, the von Kries LMS observer, and then we get these two. Then we replicate that pipeline, but we swap out the light source and swap it out for that spiky sodium light. In this setup, there are a few unsharp choices. Suppose we're building an illuminant transform for a particular project. We will choose an illuminant that comes close to the illuminant that the director of photography uses on set. Most certainly it will not be a daylight illuminant for night shot. But anyway, also we need to assume that the spectral sensitivities of the cameras, they are not known to us. So we need to base our pipeline around another observer. By using the von Kries observer, we need to trust the camera manufacturer's camera profile for the conversion to the CAE system. We know this transform is not exact, as no motion picture camera is actually colorimetric. But we are not aiming for an exact match of two scenes, but a qualitative simulation of the look for an illuminant. Why did we use the von Kries observer, not the XYZ observer? Well, because if we use the von Kries observer, then we can model also partial adaptation or partial discounting the illuminant in our spectral pipeline directly. Here, for example, we have full discounting the illuminant, and here we have slight adaptation to the illuminant, all done with spectral calculations. Okay, the sodium light example is quantitative because we do not know how the scene would have looked like under high pressure sodium light. Many of the attributes might have changed, like the diffusion of the light or the exposure of the light, so we would have maybe even a more noisy image. But now let's have a more quantitative evaluation of the illuminant transfer. For this, we are going to reuse the shots we have covered earlier, because we have also measured the illuminant spectrum for each and every shot. So let's see if we can match the 2800 to the 5600, and the 10,000 to the 5600, and the white only to the 5600, and the RGB only to the 5600. And I'm doing this exercise 2 times. One, in the first exercise, we will use not the smooth spectra as our reference scene, but the color checker SG spectral data set for our reference scene, because we actually have that color checker in the scene. So in this case, really the reference scene and the actual scene are very close, and most of those objects here have man-made pigments, which are probably quite very similar in spectral shape. Okay, so here we see the 2800 shot with a normal chromatic adaptation transform, and here with the spectral intermediate transform based on the color checker SG reference scene. It goes from here to here, right? Quite a different look. But now, more importantly, if you compare now with the spectral intermediate transform from 2800 to 5600, we can see it matches quite well for most of the spectra, especially for the color checker SG spectra, which we would guess because our simulation is based on that spectra actually. Yeah, and it works quite well. Other objects which might be metameric, so this is the white only, so the white only also works quite well. So 2800, 5600, 10,000 and white, they all look very similar. And there are only a few objects which have metameric effects, where the spectral shape, the spectral composition, is very different than the reference spectra here. And for the RGB only, it's not quite there yet. It's because it's a heavy lifting, quite heavy lifting. Remember, we're coming from here, going here, and it's close. But it's we see that for the RGB only, there are limits to that. And this is the best case where we have actually the reference scene here in place. Now I'm repeating this exercise with the smooth spectra. So if again, so this is only chromatic adaptation, that is with smooth spectra. And now when we go smooth spectra 2800 to 5600, we see it's also very good, but we get for some objects, for some other objects, we got maybe not such a good match for this one here. But if we look down here, it's quite okay. If we go to the 10,000, still okay. If we go to the white only, it's also quite in the ballpark. And now for the RGB, it doesn't fit very well. So we can see that here we're losing the reds quite dramatically here. So we are trading in accuracy, especially in the extreme cases. But what do we gain by trading in accuracy? We can examine this if we compare the extreme match from the RGB only transform with the color checker spectrum and with the smooth spectrum. And if we visualize this by using a chromaticity diagram, and what I'm going to do is I'm going to add some grain to the image so that before applying the spectral intermediate transform, so that we can see what the spectral, we can better visualize what that intermediate transform is doing. So here with the color checker SG spectra, we can see that our fitting, because it's such an extreme transformation, is not doing very well, and we might get basically bands and even maybe folds here. Whereas if we go with the smooth spectra, we can see that the smooth spectra still produces, also in this extreme case, a quite robust or quite smooth transformation. So we're trading in accuracy, but we're getting robustness. Okay. The proposed smooth spectral based illuminant transfer gets most things right and puts the shot into the right ballpark while guaranteeing a smooth spectral intermediate transform. We do not expect to predict an exact match. Instead, the resulting spectral intermediate transform can be generally applied to many scenes and still convey the look of the illuminant. And I think those trade-offs are smoothness are very wise, because we believe that we get anyway hardly any spectral data from real productions. And because also collecting spectral data is difficult and can be imprecise. And also, if we are looking for the use case of really shot matching from A to B, then there are other tools which are much more flexible and much faster for that explicit use case. Okay, let's wrap up. The most considerable challenges for this technology is the convoluted and opaque input state of the image. Cameras have unknown spectral sensitivities, and images reaching post-production have already undergone several unknown affine transformations, like chromatic adaptation matrices or matrices to an encoding color space. The spectral intermediate pipeline would benefit from a generic smooth camera sensitivity, which could be used for material already converted and adapted to a specific intermediate color space. One could think that the Academy reference input capture device could be used as such a reference observer. But the RICD is colorimetric to the 1931 standard observer, which means it provides no additional benefits in spectrally defining the actually non-colorimetric cameras. We have shown that it is possible to seamlessly blend spectral and RGB workflows within a professional motion picture pipeline, even if the acquisition is still trichromatic, or the whole reproduction is still trichromatic. With the smooth spectral reference scene, we can rest assured that we get smooth results and accurate results within reasons. We can give the creatives easy-to-use tools which operate in the spectral domain. In this lecture, we did not discuss other use cases like simulating optical filters or doing observer transfer. Both of them offer quite creative possibilities. I hope you enjoyed this lecture and you learned something from that or got inspired, and see you soon.